Alright, y'all, I'm going to be looking at question 2 from Recitation 8, and that's finding the charge per unit length of a copper rod. Alright, so here I drew the copper rod in the middle, and then I put this Gaussian surface around it, this cylindrical Gaussian surface, just because it's going to have that cylindrical symmetry, and that's where we can be relating in our lambda, our charge per unit length. So what we're going to do is we're going to find the flux. Since it's a Gaussian surface, it's going to be our Q enclosed over that epsilon naught. But also we have the equation for flux that for any given point on the surface, it's going to be the electric field at that point, coming out like this or like this. Right? And since these are parallel to these kind of faces on the other sides, we're just going to be looking at this face, the face that wraps around the cylinder. So that's going to be our 2 pi r times L. And that's our radius from the center of the rod all the way to the outside where we're looking to find the charge. That's our r here, and our L is going to be this full length that we're looking at, even though we're thinking that it's like infinite right now. All right, and for this Gaussian surface, we're going to find the enclosed charge. So since we have a charge per unit length, we're going to multiply our lambda, which is coulombs per meter, and if we multiply that by meters, or our length in meters, that's going to give us, the meters are going to cancel out, that's just going to give us our enclosed charge. So then we can set, since these are both the flux, we can set them equal, so it's going to be our lambda L over epsilon naught equals the electric field at that point times 2 pi r L. And now I'm just going to solve this equation for lambda because that's what we're looking for in this problem. So we divide through by L and multiply by epsilon naught, and we're going to get the electric field at a point times 2 pi r L times that epsilon naught, all divided by L. That's going to be equal to our lambda. The L cancels out because again we're not actually given the length of the copper rod, so we don't even have a value to plug in for that anyways. But the electric field is given and the radius is given because again that's the radius from the center of the rod to the point that we're looking at. And those are both given in the problem, so we can just plug in and solve for our lambda. So then when you plug in this 3 that's given in the equation as the electric field there. 2 pi, obviously is just 2 pi, and then 0.02, that's the radius here, that's in meters, so 2 centimeters, 0.02 meters, but it says 2 centimeters from the center of the long copper rod. Again, that's what we're looking for. And then this epsilon naught is just 8.85 times 10 to the negative 12. When you multiply all that out, you get 3.3363714 times 10 to the negative 12. And that is your charge per unit length, so that's charge per meter, coulombs per meter. And that's going to give you your answer right there, coulombs per meter. All right, and thank you all again so much for watching. Let me know if you have any more questions or if there's anything else, any other problems that you want explained, and I will do my best to explain them because I guess Sydney explains stuff.